so 1.4 notes, forgot to record at the very beginning. Here it is. Moving on. Okay, so here we have 2011 AP question number 6 that has to do with continuity. So we have this function, it's a piecewise function, so there's a possibility it's not continuous, right? It could jump from one piece to the next. We've got to show that f is continuous at x equals 0. So what we've got to do is check out those three things. So what was number 1? What was the first thing that had to be true in order for the function to be continuous? The limit had to exist. So in this case, the limit's around 0, so we have to go the limit as x approaches 0. And so the interesting part about this is I have two. I have a left and I have a right. So we need to plug it into both. When I say it, we need to plug 0 in for x, into here and here. So let's do that. Let's plug it in. 1 minus 2 times sine of 0. Anybody remember what sine of 0 is? Look up at the sine curve. You see how it crosses the origin? So if sine of 0 is 0. And I'm going to make a video about how to remember all that trig stuff. But that's an easy way, I think, of at least what sine of 0 is. So sine of 0 is 0, so this whole left-sided limit equals 1. Let's see what the right-sided limit equals. E to the negative 4 times 0. What's any number to the 0 power?
1.
1. So left-sided and right-sided limits, they equal each other, and that is the limit. Okay, so 1 is checked. So far, so good. We've got 2 more to go. All right, so 2 says, well, what's happening exactly at? Okay, we already found out what's happening near x equals 0. What's happening when x actually does equal 0? Which piece shows that? The left or the right? The left. Now, we've already plugged it in, so we already know that f of 0 is 1. So we already did that work. We don't need to do it again. And then just the last thing is to show, I'll write it here, is that they're equal. Is the answer to number 1 and number 2 equal? Yeah. The limit as x approaches 0 of f of x is equal to f of 0, which is equal to 1. Now, on the AP test, you would have to have shown all this work to get full credit. You couldn't just say, yes, it's continuous. You have to show these 3 steps. So continuity, always 3 steps. All right, we're going to look now at some times when we don't have continuity, so we know what to look for. So usually we're not concerned about continuous over the course of the whole graph. We're usually concerned about continuous at a particular point because really you don't want to check infinitely many points, right? So we're going to look at just x equals c. So first let's look at if f of c is defined. So that's great. We're going to see, okay, when is f of c undefined? This means that there is no point. So I'm going to draw a little grid here. What can happen with a graph so that there is no point where x equals c? A hole. That would be a perfect example. Okay, holes are great for limits, but when I'm talking about f of c, there's no point there. What else? So a jump would work if there were 2 holes.
Yeah.
Right. But I kind of already have that scenario. There's a different thing that could happen here. The asymptote. So if I have a vertical asymptote and the graph is going up or whatever, it doesn't even matter what's happening. There's no point where x is equal to c. So these are 2 counter examples because that's really what we're doing here. Counter examples. All right, let's look now at 2. Limit as x approaches c of f of x exists. So what we're trying to figure out is when does the limit not exist? Well, I already have an example up here. Which one of these does the limit not exist? The asymptote. So let's go ahead and redraw that just so we know it counts for both. And it doesn't matter if the graph splits or what. It's just the asymptote, no limit. What else? What else could cause there not to be a limit? And Brett, this is what you were talking about.
Yeah, the jump with 2 holes.
Yeah, if there's a jump, and there really doesn't have to be 2 holes. There just has to be a jump. They could be both holes. They can't both be points because then that would break the vertical line test and not be a function. But if there's a hole and a point,
That's right.
yeah. All right, anything else? This is the weird case that everybody forgets. The squiggly one? Yeah, where it goes, blah. Yeah, that limit doesn't exist at C. Okay, and we're looking at just C. And this is all stuff we've talked about this week. It's just kind of a recap. Okay, so that's great. Now let's talk about when they don't equal each other. Okay, so this is a little bit harder to think about when this is going to happen. Do you remember those true or false homeworks? That's what this is talking about. All right. So we're looking when maybe we have a point and we have a limit. Both of those are okay, but they're not the same. Okay? So look at this. I have a point and I have a limit, but are they the same? No. This is really the main scenario, and we see this come up from time to time, and it's just going to be a picture we're going to get more comfortable with. This is a time when f of c is the point down here, okay? The limit is up here. The limit doesn't have to be a hole, by the way. This question has been coming up a lot. The limit doesn't have to be a hole. It just has to be on the curve. It can't be separate from the curve, otherwise it's not a limit. Okay, so let's look at these three, and I want you to tell me, why is it not continuous? Is it because the point doesn't exist, the limit doesn't exist, or that they're not the same thing? So on A, what's happening to make this not continuous? Yeah, so what would I say? The point does not exist, and the way I'm going to write that is by saying f of c is undefined. This is the mathy way to say that. I'm going to switch colors here so it's easier to see. All right, what about B? What's not happening here to make this not continuous? There's a jump, so the limit doesn't exist. Now C is interesting. The limit exists. The point down here, this point right there, that exists. But what's the problem? Not the same. So we would say the limit as x approaches c of f of x does not equal f of c. They're not the same. And really, these are the three main scenarios. We've already seen these pictures. We know that the pictures look a little bit different with asymptotes. Mostly what we're going to focus on in here has to do with holes and points and all that. Okay, so let's look at this graph on number 1. And I'm going to go ahead and skip A for right now. We're going to come back to that. So on B, it's asking us to find some limits. What does the little plus and minus ask us? Yeah, so let's write that. Plus means right. I mean, it's kind of like what you think. Minus means left. So on number 2, or I'm sorry, on B, it says x approaches -2. And so you could put your pencil. The nice thing about this is if I had a pencil, I would lay it down right here. And then I would look at the plus side. That's a plus, right? Okay, so the plus means I look at the right side. So I'm looking right here. What's the y value getting close to on the right side of -2? 2 or 4? 2. Yeah, on the right side 2. And so next one, 4 with a negative. I would put my pencil right here along x equals 4, and because there's a negative, I would look on the left. Now this is actually going down forever. It's kind of weird. It's like an asymptote, but only on one side. It is weird. So what do you think? We could say does not exist. Was anybody thinking negative infinity?
Yeah.
You can say that. For just one side, you can say infinity or negative infinity. All right? But if you're like, I don't like that, I like does not exist, well, they're both correct, because by saying the limit is approaching infinity is saying the limit doesn't exist. They mean the same thing. Okay, go ahead and do the next one on your own. Try the next two on your own. Share with the buddies. See if you got the same answer that they got.
Oh, I'm sorry. The minus.
Are we in agreement? 1 and 4. And this last one, with x being approaching 0 with no plus or minus, it was important that the same thing was happening on the left and the right side. Okay, now let's look at C. Does f of negative 4 exist? This is talking about the point. If I want you to look at the limit, I'm going to say LIM. So if you don't see LIM, it's the point. So f of negative 4, the actual point right here.
Yes.
Yes, it exists, and what is that y value? 1. Okay, so now let's look at the limit as x is approaching negative 4. That's different. That's right there. It's on the curve. It's not that the limit has to be a hole, it's that it has to be on the curve. So what's the y value when x is really close to negative 4 on the curve? 2. So yes and 2. Now this comes back to discontinuous. So now we're going to take our answers here and we're going to go back to part A. We're going to answer, when is f discontinuous? Well, one of those values is at negative 4. Mm-hmm.
Okay, so part D, it's the limit exists, but it's just not continuous.
Right.
Right?
Right. The limit exists and the point exists, but they're not the same. They're not equal. That's why it's discontinuous, and we're going to write that as our answer. This was that number 3 reason, or the number 3 rule we had to check. Just a reminder, this isn't on the quiz tomorrow. We're going to have time to we're not going to finish all the notes today. Some of it we're going to do next week. Okay, where are the other places this is not continuous? What's the next value if you were tracing? You'd have to pick up your pencil. At x equals negative 2, where else? 2 and 4. These are all true for the same reason. Which reason? And so you have to tell me either the point's not existing, the limit's not existing, or they're not the same. The limit does not exist on all of these. All of these are jump functions. Did you say jump? Okay, never mind. All right. Okay, we're going to do both of these examples on the next page next week. One we're going to do as a warm-up, one we're going to do as kind of practice. Real quickly, I want to ask you about this number 4. It says, what does the left and right-sided limit mean? First of all, this is not continuous, right? Not continuous. The left-sided limits are really low, while the right-sided limits are really high. Each time, it jumps considerably. In real life, why does it jump? And I didn't read the problem, but you take your time to look at the problem and tell me. What's happening?
Okay, well, when you put in any type of drug into your bloodstream, like if you have diabetes and your blood sugar's low, okay, it's decreasing, and then when you give it spurt of insulin or whatever, all of a sudden it jumps really high.
Yeah.
And then as time progresses, it continues to go down. And then once you do that second injection, then it goes high again.
That's right. When you have an injection, this is not what happens when you take a drug, like a pill. But when you have an injection, it causes an immediate change in your blood. All right? And so this is one way of kind of using these limits and piecewise functions in a way that, there are doctors and medical personnel that have to look at these things to make sure that there's no overdose or no, over time they're not getting too much of it in their system. All right, the rest of this we're going to do next week.